To explain the concept of convergence and divergence, we will look at two examples of GP. The first geometric progression that we have has first term equals to 100 and the common ratio equals to 0.5. Now the absolute value of common ratio will be 0.5. Our first term will be 100. Our fifth term will be 100 times 0.5 raised to the power of 4. That gives us 6.25. And our 10th term will be approximately equals to 0.195. And our 50th term will be 1.77 times 10 to the power of negative 13. Now what you can notice is that the value gets closer to 0 in this case. The example of a GP, our first term is also 100, but in this case our common ratio is equals to 2, and the absolute value of our common ratio will be equals to 2. Our first term will be 100, our fifth term will be 100 times 2 to the power of 4, that will be 1600. Our 10th term will be 51,200, and our 50th term is 5.63 times 10 to the power of 16. Now this is a very big number. And what we notice is that as we move along, the values get larger and larger. So in our first example, where values get closer to 0 as n increases, we say the series converges. And in our second example, where the values get larger and larger as n increases, we say the series diverge. So why is it that sum to infinity exists only for series that converges and not for series that diverges? Now if you think about what we are doing when we are computing the sum to infinity, we are basically adding term 1 to term 2 to term 3 to term 4 and so on. Now if each successive terms get larger and larger, there will be no way for us to compute the sum to infinity, just like in this case. But in the case where the series converges, successive terms get smaller and smaller until they are negligible. And that's why we are able to compute the sum to infinity for series that converges.